binary to hexadecimal technique, we still group them into 4 bits because this is hexadecimal and starting from the right, going to your left. So for our example, we will have the answer 2BB in hexadecimal. For octal to hexadecimal, we use the technique of binary as an intermediary. That means our octal number is converted into binary in 3 bits per digit and grouping them into 4 from right to left. So you see we have 2, 3E as our answer. For hexadecimal to octal, we still use the binary as an intermediary. So we group this given hexadecimal number into not grouping but rather getting the 4-bit binary equivalent and then grouping them into 3 bits from right to left. For fractions, we have binary to decimal. When we talk about fractions, that means we see a decimal point and there are numbers to your right after the decimal point. To your left is the whole number, to your right is the decimal point. So the first number from the decimal point to the right is this one. No, this one. This one. So we are writing this one from left, right to left. So we are writing this one from right to left. So we have 1, 1, 0, 1, 0, 1. So the leftmost will have the most significant bit, okay, of our whole number here, and just to the left of the decimal point is of weight 0, and just to the right of the decimal point is of weight -1, -2, -3, -4. Then the same process, you multiply and then you add. For decimal to binary, we have this decimal number and binary number to binary number. So what we do, this one is generated such that this is 1, 1, and we place a decimal point, and this one here, this number here is multiplied by 2. Then the whole number to the left of the binary of the decimal point is written just next to the right of the decimal point of your answer. So going through your answer, then whatever is your answer here in the product, you multiply it again by 2 until such on the different number of bits that is required. So just by looking at the example, we see clearly that this is how we calculate these fractions.
So here we have a self-assessment questions. You're going to convert the following numbers to another base system. So try to solve it yourself on paper so you will be able to practice. For representation of integers, complements are used to represent negative integers. There are 2 forms of complements. We have the ones complement simply by changing zeros to ones and ones to zeros or inverting. For 2's complement, we perform 1's complement and then we add 1. Here is an example of a 2's complement calculation, so please try to check on this as for your reference. In differentiating the negative from positive numbers, the leftmost digit determines whether the number is positive or negative. If it's a 0, it is a positive sign bit, and if it's a 1, it's a negative sign bit. So if we use n bits to represent an integer, and if we use 2's complement, so we are going to use this range of numbers that can be represented by this equation. So if our base is 4, then we can have this from -8 to 7, and the 2's complement representation. So if you know this, the most significant bit will for a positive is all 0, and the most significant bit for a negative is all 1, where MSB is the leftmost number, whether it be 4-bit or 8-bit or 16-bit or 30. So here is another self-assessment question. Please try to answer this on your own and manually using paper, so you'll be able to generate correct results. In the representation of real numbers, so real numbers are represented in the form of C to the 2 to the E. So that means C is our coefficient and D is our exponent respectively. So first we are going to bias our exponent. Now in biasing, we have here shown the 2's complement for a 4-bit. Now in biasing, what you do is you change the most significant bit 1 into 0 and 0 into 1. Then that means you get a biased 2's complement for your exponent. Now in normalization, we do this with our coefficients. So here, the complete equation that we have, the first bit is, that is the S, is a sign bit. So the exponent is already the normalized 2's complement, as I have discussed in the previous slide. And the representation of the equation can be viewed similarly as the representation of integers. So remember the fractions that we have, so we can associate this one starting from the leftmost as 0.5, which is 2 to the negative 1, and then to follow with our placement. So here is an example of, self-assessment question. What is the value of the associated bit pattern? So try to check on this relative to that one of the previous slide. Now this one also, you are going to convert this into binary bit pattern. For real numbers in most computers, so for negative numbers, the sign bit is 1, but the rest of the numbers are stored in positive form. So all real numbers are assumed normalized, so that the top bit of the coefficient is assumed to be 1 and is not stored explicitly. It is called the hidden bit or the HB. So the coefficient therefore is effectively 24 bits long, including the hidden bit. With normalized numbers, the smallest coefficient is 0.5 instead of 0, while the largest coefficient is still 1 to the 2 to the minus 2 to the negative 24. So here is an example. You can go through the example. Now for our sign bit, this is 0. That means our answer should be a positive number. And our exponent, because this is binary number, so this exponent, how did we get this one? Now remember, this is already a normalized complement. So that means this is originally 0. So our magnitude is 2. So that's why we have an exponent of 2. Now how did we get the coefficient? Now remember, our HB is always 1. So this will start with 0.5 and the rest are 0. So that means our coefficient is a 0.5. Now here is another number example. Our sign bit is 1. That means our expected answer here is a negative coefficient. Okay, so here this is already a normalized answer, so exponent, so that means this is 0, so our magnitude, our exponent here is 5. Then so that's why we have 5 here, and we also have our HB1 here, so this is 0.5. Then this is, remember 0.5 is taken as 2 to the negative 1. So this is negative 1, negative 2, negative 3, negative 4, negative 5. So that means this is 0.5 plus 2 to the negative 2 to the 32. So 1 divided by 2 to the 32, you get 0.03125. So that's why you have a negative coefficient here. The rest will follow. So here is another example. questions for you to answer. Try to follow the different slides that I have discussed so you can answer. For arithmetic of real numbers, arithmetic of real numbers is made by first unpacking them into exponent and coefficient registers, like the bits for the exponent are placed in one register and the bits for the coefficients are placed in another register. The required arithmetic is performed on the exponent and coefficients, and the resultant coefficient and exponent are packed to form the real results. So here is an example, just like what we did in the previous slides. So if you are going to add this one, you have to convert this in sign bit exponent form, and then the HP and the coefficient, and then you just simply add. So you will get this answer as your reference. So the answer is here. Try to calculate it manually. For the representation of characters, characters are represented by n-bit unsigned integers, where n is usually small. So this gives 2 to the n different characters represented by integers 0.2 to the n minus 1. So we have the ASCII character set that is widely used to represent characters. It uses 8-bit codes, but only 7 bits contain data. Thus, there are 128 characters. The leftmost bit of each ASCII character can be used as a parity bit for error checking purposes. It is then set to 0 or 1 so that the total number of 1 bits in the character is odd or even. For odd, that is in the odd parity system. For even is for even parity system. So here is the table for your ASCII characters. The character is here and the equivalent decimal number is here on this column, and the hex also is there. So normally when you have this, for example, gives the 8-bit binary decimal hexadecimal code using even and odd parities for the following 7-bit ASCII characters. So you will refer to this table for finding the characters and make the odd parity checking and the even parities for the following ASCII characters. So I hope that you learn a lot for our module 1. By the way, last but not the least, before I forget, the representation of programs. So we will have these instructions and machine code, machine language more in module 4. Just an introduction. So program will have instructions in it, and all these instructions are coded in mnemonics. Okay, so we'll have more of this in module 4. Thank you.